The figure below is the.
Sir, I was getting like a little. Like,
One
the
second.
answer was a little different than
The
mine.
potential energy versus internuclear distance of hydrogen molecule in the ground electronic state. Okay, what is the value of net potential energy E naught as indicated in the figure in kilojoules per mole for D is equal to D naught, at which the electron repulsion and nucleus repulsion are absent. Okay, so basically you're going to be separating them by infinite distance technically over here. And as reference, potential energy can be taken as 0 when the electron and nucleus are infinitely far apart. Okay, mark potential energy for the 2 hydrogen atoms per mole as answer. Okay, per mole as the answer. Okay, figure below is the potential energy versus internuclear distance in a H2 molecule. Okay, what is the value of net potential energy as indicated in the figure in kilojoules per mole, E naught. Okay, all right. Net potential energy. Okay, all right. And we are going to be considering the graph from 0 to this perspective. Okay, D equal to D naught. Okay, at which the electron repulsion. Okay, as a reference, the potential energy of hydrogen atom is taken at 0 when the electron and its nucleus are infinitely far apart. Okay, so in this case here, they're asking us what is the potential energy. No, what is the exact question here? As a reference, the potential, what is the net value of net potential energy E naught? Okay.
Total potential energy for 2 hydrogen atoms.
Hydrogen atoms.
Per mole. Yeah.
Per mole. In that form where they are going to be, what to say, in the molecular form. Right. So when you're in the molecular form, they're going to be at the lowest energy level at that particular case. With respect to that, how much is it going to be? So for instance, if I'm going to be having, say, this is the reference line here. This is going to be giving me my E naught marking here. Okay. I'm going to be having the energy level at this level is going to be 0 at infinite distance. And we are going to be having the graph basically going as usual like this. Something like this. Okay. And we're going to be having this value being asked. And this is going to be for H2 molecule. Okay, all right. Okay, and they're telling us D is going to be the distance. Okay, all right. So in this particular case here, we're going to be having hydrogen molecule. We are asked over here, 2 hydrogen atoms are basically interacting. This is also an old JEE question, is it?
Yes, sir. Yeah.
Which year is this? I would like the actual version itself.
Just a second.
Yeah.
2020, sir. Paper 2.
2020, paper 2.
Yes, sir.
Okay. So in this year, we are going to be having. This is a full question. Good enough. We'll directly use this photo itself. Okay. So we are given that we are going to be having a hydrogen molecule over here, and we are having interaction happening. And this is going to be for ground state. Now, when you're going to be talking about a molecule's ground state, what is going to be the lowest energy level for the molecule? This is going to be hydrogen molecule location, correct? Or a ground state scenario. So what is going to be the distance here? We're going to be having to calculate that particular value out first. So if I consider the hydrogen molecule, H2 molecule, what type of an interaction is it expected to be? It's expected to be a 1s interaction.
Yeah.
Correct. So it's supposed to be a 1s sigma 1s. Fair? So if it's going to be a 1s sigma 1s, then in that particular case there, the first shell 1s is going to be, of course, n equal to 1. What is the distance of the electron in this particular case here?
Or not?
0.5 to 9 angstrom.
Yeah.
Correct?
Hmm.
So you're asking us what is going to be the potential energy of the electrons present at this stage over here, right? At this location here. Potential energy, what is the formula for potential energy?
Minus KQ.
Q2 by R. This is per electron. So we're going to be having two of them here, correct?
Yes, sir.
So we're going to be having, in this particular case here,
2 into
two
L.
electrons. How much? Because each of those two electrons are respectively at a distance R from one of the nucleus. But they are going to be at very large distance to the other nucleus as a general understanding. But that is not the case here, correct? Because both the nucleus electrons are going to be in the same region. That's what ground state they are interacting means, correct?
Hmm.
Think for a second what's happening there. We are having a 1s sigma bond being formed over there.
Hmm.
So we are going to be having one nucleus present here and one nucleus present here. We'll be having both the electrons present over here. And this distance is going to be 0.529 angstrom. And we'll also be having this distance also as 0.529 angstrom.
Hmm.
You understand the idea here clearly? So basically, we are going to be having hydrogen atom number A nucleus.
Yeah.
This is hydrogen atom B nucleus.
Hmm.
Fair so far?
Yes. Yeah.
So if this is going to be the case, what will be happening now then?
Now it'll be KQ and Q2 by 2 into 0.529.
Right? So go for it now then. How should you proceed now then?
Into 2 by 2, that
Having
cancels
KQ and Q2 by R over here. In that R there, we will end up having
2A naught.
Sorry?
It'll be 2A naught, right?
Sorry? 2?
R will be 2A naught. 2 into 0.529.
No, R will be the same. R will be the same because the distance is the same. The electrons are going to be at distance of 0.529 only. R is going to be, if you take it as 2A naught, that is going to be distance between the two nuclei. Na?
Yeah, that's what we need to do.
Why do we need that?
Then why are we not considering the nucleus attractions?
It's not going
Repulsion.
to be because look at what is being taken here. This is going to be electron, at which electron repulsion is absent over there, and nucleus repulsion is absent here. You're going to be assuming that not D for D naught over here. At that point, we are going to be having the perfect level, which is going to be achieved over here, which is going to be at this point here. This is your D equal to D naught point here. But this energy here is for the electrons here, maximum total potential energy for two hydrogen atoms per mole. Oh, they are not asking that way. Potential energy of hydrogen atom is taken as 0 when its electron and nucleus are infinitely apart. Net potential energy.
Sir,
This
what?
is for the entire system only. Entire system के लिए means we'll have to add and subtract over here. Let's try out what क्या आता है. So we'll end up having two electrons here. For them, the distance is going to be only what I say R over here. So nuclear repulsion also we'll have to consider. Electron repulsion also we'll have to consider now. So let's subtract out the nuclear repulsion. What is going to be nuclear repulsion there? That will be again KQ1 Q2 by R. So we'll have K1 into Q2 by R here. In this here, I'll be having Q1 is going to be 1 electron because it's a nucleus.
Q2 also.
Q2 is going to be 2 though because there are 2 electrons present there.
Okay.
And R will be 0.529. And this will be with a negative sign. And this will be with a positive sign. Okay.
Into 2, right? Because 2.
Sorry?
Into 2, right?
Why do I need to do into 2 here? Repeat.
There are two hydrogen atoms, and aren't we considering both their attractions with the electrons?
Fair. Into 2. There are 2 nuclei definitely. Each one is going to be having this attraction as well. So attract nuclei 1 with the 2 electrons here is going to be this much. Nucleus 2 with the 2 electrons is going to be this much. Good. Okay, cool. Already into 2. And next is going to be the repulsions there. This is attractions. So it's a negative value. Repulsion wise, you're going to be having nuclear repulsion. We can't talk about electron repulsion because they're in the same orbital. So we are not going to be assuming that part over there. We're going to neglect that there. So nuclear repulsion wise, we'll have K into Q1 into Q2. This will be 1 electron worth charge. This will also be 1 electron worth charge divided by, in this case here, I'll be having 2R.
2R, yes. This is a repulsion again.
Repulsion.
Minus.
So plus
No,
here.
no, plus.
So net value will work out as how much over here? We'll be having
4 by 2, 4 minus by 2.
4K into E squared divided by R naught minus sign के साथ, and this will be plus Ke squared divided by 2R naught. Okay, I can write it as this will be Ke squared itself. This I'll make it as by 2R naught. Now I'll make it 8. So this works out as minus 7Ke squared divided by 2R naught. This works out as 3.5 Ke squared by R naught with a negative sign. Per mole में, if I have to calculate, this will work out as multiplied by Avogadro number. It works out as minus 3.5 Ke squared R naught multiplied by Avogadro number. Electron value of net potential energy indicated in the diagram. We are talking only for the electron. This is for the entire system. Only for the electron now, it will be just this, which will work out as 4Ke squared by R naught. Only for electron if I consider. How do I get there? Only for electron. In that case, it will be 4 into K into E squared by R naught, which works out as multiplied by Avogadro number, of course. So that will work out as much, then it will work out as 4K E squared by R naught. So substitute तो करना पड़ेगा टूडिए, ये substitute करके तो कर सकते हैं तो.
So but
Cannot be without substituting.
Just a second.
Do we have a solution available?
Yes, sir. Yeah.
Send me the photo of that. I'll be able to make more sense of it directly.
They didn't consider like one second.
That's what I'm looking at. Two possibilities here. Now I want to know which one is even working closer. Is it this one or is it this one which is closer? And what are they going with?
Yeah. Send it.
SK Q2 by R, okay. Minus K is got potential energy of one hydrogen atom in ground state, okay. They're not considering nuclear repulsion here, first of all. And they are taking one hydrogen atom in ground state, okay. Two hydrogen atoms or one molecule of hydrogen. Okay. One more thing they are doing here is they are assuming that each of these atoms are just individually in ground state and the electrons are not in the middle. So they are basically not taking it like this. They are considering that each nucleus is only attracted to one electron at a time. Doesn't make sense logically. They are only taking two individual hydrogen atoms, not in a molecule here. Because if you consider it as a molecule, the two electrons should be attracted equally by both the nuclei. That's the idea. Here we are not considering it like that. So what they have done is acceptable over here from the point of view of if I consider it as two individual hydrogen atoms. Not a molecule. So if I'm considering them as two individual hydrogen atoms and not as a molecule here, then in that particular case, this is all acceptable. So this is going to be meant for at a distance d equal to d naught, which is going to be at this infinite distance. In under that condition, then this is going to be applicable. Let's have a look at the question again. That means I did not read the question properly. What is the value of this? What is the value of net potential energy E naught for D is equal to D naught, at which the electron repulsion? The question is valid only, da. Their answer is also not correct. Actually, not wrong here. Their answer is correct here. I assumed wrong here. I assumed that they wanted at this distance over here, at this point here. That is a mistake I made here. My
They
entire
wanted D naught.
huh?
They wanted D naught, right?
They wanted D naught.
But then they only give that. It's, I mean,
The rest of the question is nonsense over there. Don't read the remaining part that the reference and all is not meaningful there. The real part of the question which is meaningful over here is what is the value of net potential energy E naught? This E naught value here. Don't care about what is the scale which is taken. There is no scale. All right.
okay.
They're asking what is that net value E naught, at which is you're going to be having inter-electron repulsion is absent and nuclear repulsion is absent. So at this point here, you're going to be having only two individual atoms, only two separate hydrogen atoms.
Won't that be at infinity?
Technically, it is at infinite distance from each other, but you can basically say at ground state independently.
So then why? Oh, okay. I see.
Sorry, what?
Okay. Nothing. Sorry, got it. I was.
The idea here is by giving this graph, they're just confused. That's
Yeah,
all.
D naught they gave. So I was very confused. I thought it was like finite something.
That is not the point at all. The D naught is not a finite.
Yeah.
It is just a random infinite distance.
Yeah.
They're asking at that what is going to be the case. So when you treat them as two individual hydrogen atoms, not a molecule, at distance d equal to d naught, technically infinite distance.
Okay.
Effectively,
And
what
that
is
makes
going to be
sense.
happening here? You're going to be having no electron repulsion and no nuclear repulsion as well.
Only two nuclears and electron repulsion attractions.
Yes, correct. Huh? So basically treat them bluntly as individual species over there. So when you treat them as two individual atoms,
Multiply by 2 again.
none of this nonsense applies. This is for the molecule. This is for molecule assuming ground state. Is 1s. But we don't need to do any of that assumption. It's a much simpler thing. They're asking only for the individual atoms over there. So very straightforward, get it done. For the molecule, if you end up assuming what to say, this particular type of conditionality, then whatever we did applies over there. This is going to be for the nuclear repulsion. There should be one more aspect which has to be added in for the electron repulsion also.
But then we neglected that.
We neglected that in this case here.
But then the,
this is electron nucleus attraction, correct?
Yes, sir.
We neglected electron repulsion because that is going to be something which I assume would be taken in the Pauli's exclusion principle anyway. So that's basically the idea here. So if we are going to be considering them as individual atoms, then whatever they have done perfectly applies. It will simply be very straightforward. If you take them as individual atoms, it will be minus k e squared by r naught per hydrogen atom.
Yeah, per hydrogen atom, yes.
That's it. So you're going to be having two separate atoms over there, implies 2 times minus k e squared by r square, g by r naught.
Okay, got it.
2 hydrogen atoms.
That's the answer. Into it.
And if you want to convert it into what to say the per mole type of thing, all you have to do is multiply by Avogadro number. Fairly straightforward.
Okay, sir. Yeah.
You understood the idea here?
Yes, sir. Hmm.
I was stupid enough to go for a much more complicated case, but yeah,
Yes, sir.
mistakes are mistakes.
Yes, sir. Sir, like in this paper, I just saw like another question.
Mhm.
Like I think this is chemical bonding. Here, do you have to like memorize the ionization enthalpies of like
What's the
you
question?
know, sir, do you have the paper open? Or
I am about to download it. Tell me the question.
sir, it's like the first, second, and third ionization enthalpies I1, I2, I3 of four atoms with
Question number, I'm
atomic
having the J Advanced paper open in J Advanced website. Question number
2020 paper. First question, sir, for me.
2020, first one. Okay. IE values. Okay.
Oh yeah.
First, second,
Yes.
and third IE values are I1, I2, I3 of four atoms. The atomic numbers n plus 1, n plus 2, n plus 3, where n is less than 10. Our tabulated below. What is the value of n? Okay. Why do you need that? You need to just guess.
Yes.
Look at it. N plus 3 la kya ho raha hai? You're going to be having that being something where the ionization energy is increasing after the second one
Yeah.
dramatically. That means that's group 2. N plus 2
Oh, okay, okay, okay. I remember now. Okay, okay.
N plus 2 is your group 1 because
Uh,
I value is going to be much higher after the first one.
yes.
The first
Okay,
one is
okay.
lost very easily. Second one is lost much more difficultly.
Okay, yeah, now I remember. Yes, sir. I
Much
got
more
it.
difficultly. So that is group 1.
Yes.
So use that kind of common sense and apply.
Oh yeah. My bad. Yes, sir. Yeah.
So N plus 1 is what? Noble gas already.
N plus one.
N
Yeah.
plus 2 is group 1. N plus
N
3
plus
is
two
group
should be
2.
11.
So N plus 1 is your noble gas.
Yeah.
So N is
Yeah.
10. See, N is 9.
N
Or
is
N
9.
can
Yes.
be 2. N can be 1.
N can be 1.
Yeah, N can be 1 also. Right. But the problem there is if N is 1,
N is 1,
then
then
I
the
can't
first.
lose 3 electrons.
Exactly. Yeah.
So
Yeah.
N is not going to be 1. So N has to be 9 in this case.
9. Yeah. Okay. I was just wondering. Okay. Hmm.
You understood the method there?
Ah, yes, sir. Yeah. I just.
Okay. Anything else to discuss in this paper here?
I didn't think a few of these questions came in our paper once. Hmm.